So more trig identities. These ones are for C. So hopefully from CT you'll remember our identity that we already know, that sine squared x plus cos squared x is always equivalent to 1, and that three-lined equal signs means that no matter what value I give x, in fact, that will always be true. And we looked at it by looking at a right angle, so hopefully you'll remember this, but if not, I can remind you now. We drew a right angle triangle and we labelled the hypotenuse 1. And we labelled the bottom corner x, but it, to be honest, doesn't matter. We can label either of the other angles other than the right angle x. And then we thought about how we could describe the other two sides. So the side opposite the angle we know from GCSE is called the opposite, and the one next to the angle is adjacent. Now we know some equations, I guess, that link these things to the hypotenuse, don't we? We know that sine of our angle x is opposite over hypotenuse. We know that cos of x is adjacent over hypotenuse, and I'm going to stop there, but obviously tan is opposite over adjacent. So we know that our hypotenuse is 1 in both of these cases, so actually I can get rid of my hypotenuse there in both of these equations, if I needed to, and replace that with 1. Now, anything divided by 1 is just itself, so in fact I can just completely get rid of my 1. So now we have expressions for the opposite and the adjacent just by using GCSE trig. The opposite we could rewrite as sine x, and the adjacent we could rewrite as cos x. Now you know something else from GCSE that links those three sides, and that of course is Pythagoras, and hence why this is a Pythagorean identity. So the two short sides squared added up is the long side squared. So let's do that. Let's do sine squared x add cos squared x, and we are claiming that that is 1. Turns out, of course, that is true, and we'll have to look at the unit circle to prove it, but we will do that in class. Okay, what happens then, because we might idly wonder this, what happens if I change the location of the 1? So rather than having a 1 on my hypotenuse, I might, maybe because I've mislabeled because I'm tired, or maybe because I'm just inquisitive about it, what happens if I move the location of that 1? Well, we can still rewrite our sides in terms of sine x and cos x. So, quick reminder then, we know that sine x is the opposite over the hypotenuse, and we know that cos x is adjacent over hypotenuse. So what have we got going on here? Well, our opposite is now 1. That doesn't change because it's opposite the angle, and we don't know anything about our adjacent, but we probably want to find out, and we don't know anything about our hypotenuse either. So we may as well use the equation that has opposite in it, and that would be sine. And let's fill in the information we know. So sine x is opposite, which is 1 over the hypotenuse. Okay, so could I rearrange that to get an expression of the hypotenuse? I certainly could. Multiply both sides by the hypotenuse because it's just a value. Hypotenuse, lots of sine x is 1. And that implies that the hypotenuse, just by dividing by sine x, is 1 over sine x, which we now know is cosec x. So our hypotenuse we can relabel as cosec x. What about our adjacent? Well, this is going to be a little bit more tricky. We're just going to have to persevere with the algebra a little bit. So let's just get rid of all of this. So adjacent then, we know we can find an equation with adjacent in it by looking at cos. So cos of our angle, which is x, is the adjacent over the hypotenuse. Now, I didn't know either of those a couple of minutes ago, but now I know what the hypotenuse is. The hypotenuse is cosec x or 1 over sine x. I'm just going to use 1 over sine x just for a moment because I think it's easier to see. So cosec x is the adjacent, cos x is the adjacent over cosec x, which is also 1 over sine x. Now if I want to get an expression just for the adjacent, what I need to do is multiply both sides by the hypotenuse, which is 1 over sine x. So that's going to give me 1 over sine x lots of cos x. I'll write that a bit neater. Cos x. And that's our adjacent. I can simplify this multiplication here to be cos x over sine x, which looks like tan x upside down. Haha, helpful. Tan x upside down, that's 1 over tan x, it's the adjacent, and so the adjacent is cot x. So this adjacent now we can replace. That is cot x. And now I can just use my Pythagoras again to give me a new identity, so a new expression in terms of cot x and cosec x. So 2 short sides squared added up together. So cot squared x add 1 squared, which is 1, is cosec squared x. 1 in a cot is cosy. Okay, I'm going to leave you to try this one for yourselves. I recommend you do it, and we will check what you get in class. So you need to follow the exact same method as you did in the last slide, and you should get a new expression, and it should contain a 1, a sec squared x, and a tan squared x. Okay, there is another way of deriving these, and that is to consider what would happen in a single case, so I'm going to take one of those lines out, and dividing through by either sine squared x or cos squared x. Now I'll show you what happens with the sine squared x one, and then hopefully if you divide through by cos squared x, you should get your other expression that you found in the previous slide. So let's take each part of our equation here and we'll divide it by sine squared x. Now obviously we have to do it to everything, cannot miss anything out there. So that will hold in that case. So sine squared x over sine squared x, that's 1. Cos squared x over sine squared x is the same as cos x over sine x all squared, which is cot squared x, and 1 over sine squared x is the same as 1 over sine x all squared, which is cosec squared x, and there's our identity back again. So I'm going to leave you to divide by cos squared x, and hopefully that will give you 2 ways of finding that other one and you know you're right.